Hare Krishna everyone. So in today's lecture I am going to start with your failures of Bohr's atomic model, that is failures of Bohr's atomic model. So we will see what are the failures of Bohr's atomic model. Okay. So the first one is Bohr's atom model does not give Bohr's atom model does not give any idea about what, about electron distribution in an atom. Okay. The second one is your failure of Bohr's atomic model is in this atom we have two rival theories. What we found out from your Bohr's theory, that in the atom we have two rival theories. What are the theories? That is classical and quantum theories. I will explain what are the rivals, in which context both the theories contradicts each other. That is the equilibrium. The equilibrium is governed by the classical laws, whereas the emission and absorption of radiation is explained by quantum theory, quantum rules. Okay. So the third failure of the Bohr's atomic model is the Bohr's model could not explain the fine structure spectra. The fine structure splitting. Okay, the fine structure splitting. Bohr's atomic model was unable to explain your fine structure splitting. The fourth failure is Bohr model does not give any idea about what? Idea about intensity of your spectral lines. Okay. These are the four failures of your Bohr's atomic model. Then we will look into your Wilson-Sommerfeld's quantization rule. Let me have the pens. Yes. What we are going to look into? Your Wilson-Sommerfeld, very important for your exam, quantization rule. Okay, Wilson-Sommerfeld quantization rule. What does it say? It says for any physical quantity, let me write the law. For any physical quantity or physical system, you can say for any physical system, let it say as system, for any physical system. Okay, for any physical system in which the coordinates qi I am taking qi as your generalized coordinates are periodic functions of time. Okay, then there exists a quantum condition for each coordinates Okay, so what is that condition or quantum rule? The quantum condition is what is that? Is your integration over pi into dqi is equal to your nih. Okay, let me make it a box, give it a equation number 1, where phi is the linear momenta associated with qi, where pi is your momenta associated with qi. Okay, is it clear to you? Yes. And ni, and here ni, I have forgotten to tell you, and here ni is your quantum number. Okay, let us see the application of this Sommerfeld quantum rule. There is certain applications of Wilson Sommerfeld quantum rule. Wilson's Sommerfeld quantum rule. Okay, let me look into it. What are the applications? The first one is derivation of Planck's quantization of energy. What is the first one? We will derive Planck's quantization of energy through your Wilson-Sommerfeld's quantum rule. Let me show you how can we derive derivation of Planck's quantization of energy. Quantization of your energy. Okay. So let us take a one-dimensional harmonic oscillator into consideration. That is for one-dimensional harmonic oscillator. What I have is the total energy is equal to sum of kinetic energy and potential energy, isn't it? In place of kinetic energy, I can write as that implies your E is equal to, I can write px square upon 2m, isn't it? Yes, that is the kinetic energy expression. And potential energy as half kx square, isn't it? Yes. I can further write it as, if I take E into the denominator of RHS, then what I will get? Px square upon 2me is plus your x square upon I have taken k into your denominator, that is 2e upon k. Okay, isn't it? Is equal to 1. I can further write it as px square upon root over of 2me square plus x square root over of 2e upon k square is equal to e 1. You have seen this type of equation in your previous classes or in some other examples. What is it? It is the equation of ellipse equation. Okay, where the value of your semi-major axis is how much? Semi-major axis is root 2me and your value of semi minor axis semi minor axis is how much? Root over of 2e upon k. Yes. Let me draw the elliptical path for you. That is, let me change the color of the pen. Yes. This is, sorry. Let me draw it again. Yes. This one is my semi major axis. This is having length root over of 2me, and this one is my semi minor axis having length 2e upon k root over. Okay, do you get it? Yes. And remember, this is my px and this is my x direction. Okay, let us proceed further. Now, by Wilson Sommerfeld quantization rule, what I have, quantization rule, we have integration over Vx dx is equal to your nh, isn't it? I can further write it as pi ab nh, where a is your semi major axis and b is your semi minor axis. So what it will give us? Pi, putting the value of a, that is 2me root over, and value of v, that is 2e upon k, is equal to your nh, isn't it? Let me solve it further. That is pi, both are having 2e, so 2e taking outside, and what we have left with? M by k. This is equal to nh. So E will be equal to your nh upon 2 pi and multiplied with your k upon m, isn't it? Which is equal to, I can write it further as E is equal to, if I will substitute your h upon 2 pi, that is h cot, and k by m, I know that is omega, it will become nh cot omega. So E will become, E is equal to your nh cot omega. I can write it further as E, if I will substitute here, omega is equal to 2 pi nu, where nu is your frequency, so I will write it as n h upon 2 pi, and this is 2 pi nu. So it will become your 2 pi getting cancelled, nh nu, isn't it? So E is equal to nh nu. So this is my Planck's quantization energy. So hence I derived the Planck's quantization energy from your Wilson-Sommerfeld quantization rule. Okay, derived. Okay, yes. So this was my first derivation, and the second application is derivation of your Bohr's quantum condition. Bohr's quantum condition. If you remember, I have said you that the Bohr's quantum condition is what? That is, your MVR is equal to nh upon 2 pi. That is, angular momentum is equal to nh cot. Okay, where n is integer. That is, if I will write it as MVR is equal to your nh upon 2 pi. I will have to derive this from your Wilson-Sommerfeld quantization rule. So write it. So Wilson-Sommerfeld quantization rule, we have integration over pi dqi is equal to ni into h. Give it equation number 1. Let your qi is equal to theta, so pi is equal to p theta. This is my angular momentum. Okay, and ni is equal to n. So equation 1 will become what? root over integration of p theta d theta is equal to nh. So it will become p theta taking outside and d theta is equal to nh. So integration over d theta, it will become the total angle, that is 2 pi is equal to nh. So p theta is equal to nh upon 2 pi. This is my Bohr's quantum condition derived. Okay, derived. So this was my second application of your Wilson-Sommerfeld quantization rule. Let me do the third one for you. We have the third application, that is your de Broglie's interpretation of Bohr's quantization law. De Broglie's interpretation of Bohr's quantum law. Bohr's quantum law. Okay, let us see. From de Broglie's hypothesis, you all have known that de Broglie's hypothesis, what was it? Hypothesis is your lambda, that is wavelength of electron, is equal to your h upon p, or I can write it as h upon mb, as p is equal to your mb. So further I can write it as mb into lambda is equal to h, isn't it? I can write, if you remember, we have mbr is equal to nh upon 2 pi. So I can write it mb as your nh upon 2 pi r. So let's substitute here. So it will become nh upon 2 pi r into lambda is equal to h, isn't it? So it will become 2 pi r will become what? In lambda, isn't it? Yes. So this is, I can write it as circumference is equal to your n into de Broglie's wavelength. This isn't a application of your Wilson-Sommerfeld quantization rule, but this is the de Broglie's interpretation of Bohr's quantization rule. How de Broglie interpret the your Bohr's quantum model. Okay. Yes. So I can write it as, if I will have to write, I can write the conclusion from this. The electron wave can be adjusted around an orbit only when the circumference, the condition, okay, the circumference of the orbit can contain exactly an integral multiple of your de Broglie wavelength. Okay, this one is the condition, or you can say the conclusion from de Broglie's interpretation. Okay, so we'll see a very important topic here. Okay, this one is Sommerfeld extension for Bohr's model. Okay, where we are at our Sommerfeld extension of Bohr's model. Okay, let me talk about it. Yes, Sommerfeld has considered that the electron could move in elliptical orbit also. In addition to that, Bohr considered the circular orbit. Okay, let me write. Sommerfeld has considered the electron could move in elliptical orbit also. orbit also. In addition, in addition, in addition to the Bohr's circular orbit, Bohr's circular orbit. Remember, in Bohr's postulate, we have discussed that the electron moves around the nucleus in stationary circular orbits. But Sommerfeld has considered the electron could move in elliptical orbit also. Yes. So, let me take an elliptical path. Let me take an elliptical path like this. Okay. Let's suppose here is my nucleus and one of its foci. Here is my nucleus, let us consider, and here is my electron, and the coordinates we have to take is your polar coordinates, that is r theta. Let me show you, let me write it for you. Let an electron is revolving around nucleus in elliptical orbit with nucleus at its foci. Okay, let r theta are the two coordinates which are periodic function of time, periodic function of time. Okay, periodic function of time. Okay, suppose p theta are two associated momenta. Let's suppose PR and P theta are two associated momenta. Okay, momenta. Okay, as we have studied Wilson-Sommerfeld quantization rule, so from Wilson-Sommerfeld quantization rule, what I have, that is integration over PR dr is equal to your nr into h. Give it a equation number 1, and I can further write it as integration over your p theta d theta is equal to n theta h. Let us take n theta as k h. Okay, this is equation number 2, where n theta I have taken as k. Okay, so where give it a equation number 2. Yes, I have given it, where nr and k, that is your n theta, are radial and azimuthal components, azimuthal numbers. Okay, respectively. So if I get the solution of your equation 2, that will be will be your integration over p theta d theta, and that is k into h, will be equal to your p theta getting outside and d theta is equal to kh, where d theta integration will become your 2 pi is equal to kh. So what it will become, it will give rise to your p theta is equal to kh upon 2 pi. Give it a bracket, name it a equation number 3. And further I have p theta. If you have known that p theta is your nothing but m r square theta dot, I can further write it as p theta as m r square theta dot is your derivative of theta with respect to time, d theta by dt. Give it a equation number 5. Give it a equation number your 4, and this is your 5. Okay, so, and also PR is how much, mr dot r dot is nothing but your dr by dt. I can also write it as dr upon d theta and d theta upon dt, isn't it? Yes. So it will become pr will become your dr upon d theta, and in bracket you have taken m d theta upon dt. I just arranged that. Pr will be equal to your dr upon d theta into p theta upon r square. This one I have taken from your equation number 5. From equation number 5 you can write equation number 5. From equation number 5 I have written it. Make it a box, and give it a equation number, your what? Equation number 6. Yes. Let me proceed further. So dr I can write dr as your dr upon d theta into d theta, isn't it? Give it equation number 7. From equation number 7, 6 and 1 you can get that integration over p theta r square into dr upon d theta into dr upon d theta into d theta will be equal to your NRH. Let me show you that equation number 1 we have this PR dr is equal to NRH. So in place of PR and dr I have substituted these values. PR, in place of PR I have substituted p theta by r square into dr by d theta, and in place of dr I have substituted dr by d theta into d theta, and NRH as before there. Okay, so it will become your p theta integration over 1 by r dr upon d theta whole square into d theta is equal to your nr into h, isn't it? Make it a box, okay. Give it a equation number, your 8. Yes, equation number 8. So what we have, the polar equation of ellipse, we have polar equation of ellipse as L upon R is equal to your 1 plus E cos theta, where E is your eccentricity. This is your eccentricity. Okay, this is your eccentricity of ellipse. Okay, so taking logarithm on both sides, taking log on both sides, we get both sides, we can write it as ln L minus ln R will be equal to your ln 1 plus E cos theta, isn't it? Yes. So now differentiating with respect to theta, I can get this L. If I differentiate with respect to theta, it will become 0, and this one will become 1 by r dr upon d theta will be equal to your 1 upon 1 plus E cos theta into your minus E sin theta, isn't it? As your derivative of cos theta is how much? Minus sin theta. Okay, that implies what it will become? 1 by r dr upon d theta is equal to your E sin theta upon 1 plus E cos theta. Okay, give it equation number 9 and make it a box. Okay, from equation number 9 and 8 we can see that p theta integration over 0 to 2 pi E square sin square theta upon your 1 plus E cos theta square d theta is equal to your NRH. Okay, so it will become p theta 2 pi, within bracket we have 1 by 1 plus E square root over minus 1 in bracket NRH. Okay, isn't it? So it will further become your 1 by root over of 1 minus e square minus 1 will be equal to your nr upon k, as you have the value of k as your how much, the value of k is your p theta. You can write from here, okay, in equation number what I have mentioned here. Yes, p theta is your kh upon 2 pi. P theta is your kh upon 2 pi. So I have write it as p theta. As p theta, I can write it as kh upon 2 pi, and here is already a 2 pi, so 2 pi getting cancelled, and you have taken kh to this side, so it will become nr upon k. H getting cancelled, okay, h getting cancelled, it will become nr by k. Do you get it? Yes, I can write it. You have known that we have 1 minus e square, that is eccentricity square, is equally to your b square by a square. So I can write it as your a square upon b square root over minus 1 is equally to your nr upon k. So it will become your a by b minus 1 is equally to nr upon k, isn't it? Yes. So I can write it as a by b is equal to 1 plus nr by k. Okay. So it will become b by a is equal to your k by n, where n is your nr plus k. Okay. This one is my last conclusion. This is equation number 10. Give it equation, and this one is my equation number 10. So this equation number 10 gives us the quantum condition for elliptical orbit, as Sommerfeld modified the Bohr's circular orbit as elliptical orbit. So we have required the proof, and we got the proof as elliptical, the quantum condition for your elliptical orbit. Okay. So out of all the possible ellipses, so where the electron moves, let me write, out of all the possible ellipses, the electron can move only in those ellipses for which the ratio of okay, we have to write the quantum condition. The condition here is the condition for elliptical orbit. We have the particular ellipse in which the electron can move where this condition is satisfied. This condition means your ratio of B and A will be equal to your K and A. Okay, the ratio of the minor to the major axis is equal to the ratio of two integer is nothing but your ratio of K and N. Okay, do you get it? This is the quantum condition for which you have the elliptical orbit. So let me highlighted the quantum condition. This one is my quantum condition. Remember this one. The ratio of your minor axis to major axis is the ratio of two integers. Okay, so for today I have all about this. Let me conclude the class here. So thank you for watching. Do subscribe to my channel and like and share with your friends. Thank you.